Hello everyone, MK's here. This is the session on number theory for which you have done so many classes with me on number theory. You have studied also a lot. The chapter I'll be discussing with you is congruences. Congruences in number theory is a very important topic in number theory, and I hope you all have heard about cryptography. Cryptography, this congruency plays an important role. So what congruency talks about? It talks about the relationship between two integers, or you can say three integers, when two of them divided by the third one, they will leave the same remainder, or when one of them divided by the other, then remainder will be the third one. If it is not clear, I will be giving you an example. Wait for that. But what I want to say, you be ready with your pen and paper to do congruency, to learn congruency with me here. So let's start. What is congruency? Two integers a and b are given the simplest definition here. Two integers a and b are said to be congruent modulo m if they give the same remainder on division by m. For example, 13 and 48 are congruent modulo 5. Why? Because remainder, when 13 divided by 5, this remainder will be what? 3. And remainder, when 48 divided by 5, this is also 3. You understand? So these two numbers, 13 and 48, when they are divided by 5, they leave the same remainder. We are talking about 13 and 48, okay, and then 5 dividing both of them, and we can write that 48 congruent with 13 mod 5. You understand? Because 48 when divided by, just a minute, just few seconds I'll take to put the light on. Sorry for the pause. So 48 and 13 when they are divided by 5, they leave the same remainder 3. We will write 48 congruent with 13 mod 5. Hope you have understood. We can write 9 congruent with 29 mod 10. You will say that why 9? 9 is smaller than 10. Okay, if you divide 9 by 10, then remainder you assume that 9 only, because you cannot divide 29 when you divide by 10. The remainder is 9. That's why 9 is congruent to 29 mod 10. You could have also written this form. 29 is congruent with 9 mod 10. Okay, same thing. Because 29 leaves remainder 9, and 9 not divisible by 10, so remainder is 9 over there. You can make another observation here. to define congruency, we can say that 5 in this example, 5 divides the difference of 48 and 13, and here 10 divides the difference of 29 and 9. Am I clear? Hope you have understood. So congruency we can state this manner: two integers related to each other in such a manner that when divided by third integer they leave the same remainder, or two integers related in such a manner that their difference is divisible by the third. Then we say that one integer congruent with other mod m. Mod means modulus, but it is not modulus function. This mod m, this number is going to divide the difference or going to divide them separately. Take few more examples. Can we write 47 congruent with 21 mod 13? Yes, because 47 minus 21 is 26. 13 divides 26. So this is correct. And 47 divided by 13. The remainder, if you write, what's the remainder? That is 8. Remainder when 21 divided by 13, that is also 8. So clear with this example also, that difference divisible by 13. Individually, they leave the same remainder when divided by 13. Now, can I say this thing? That A is congruent with B mod A minus B. Very important observation. I will say this is a very important observation. A congruent with B mod A minus B. Why? Because A minus B, as A minus B is divisible by A minus B, so in two integers A and B will be related to each other with this relation: A mod A congruent with B mod A minus B. Clear? Understand? So this is a important observation. Okay. Next, A congruent with 0 mod M. We can state directly M is dividing A. Why? Because we go by that definition. If A congruent with 0 mod M, what does it mean? A minus 0 is divisible by M. So this implies that A is divisible by M. Okay. This is another good observation. You write observation 1 here, observation 2 here. A congruent with 0 mod M implies if you ever get this. Like I am just writing one example. 50 congruent with 0 mod 10. Because 50 divisible by 10. You can state that this 0 is the remainder. You can state here that B is the remainder when A divided by A minus B. You can also state that 21 is the remainder when 13 divided by 47. No, it is not true, because 21 is larger than 13. That's why you go by the first definition. They leave the same remainder, meaning it's same. So by now we will be remembering this thing, that A congruent with B mod M implies that A minus B is divisible by M. Also that another implication will be there, implies this thing also, A and B leaves the same remainder when divided by M. Just keep this concept in your mind. Now let us go for third observation. Okay, this is also very important. Observation 3. What is that? A congruent with B mod M if M divides A minus B. This is already stated. Now can't I say that A minus B by M is an integer? This is an integer. That integer we are going to take Q. Q stands for what? Quotient. So we can write A minus B equal to M cube. This implies A equal to B plus M cube. Clear to you? So this is going to be added. In our observation, we have seen that A and B leaves the same remainder when divided by M, equivalent to state that A equal to B plus M cube. Clear? Understood? Let us go for next observation. These are not observations, these are rules which you can follow to solve problems on congruency. Okay? We are going to prove these also. A congruent with B mod M. Can I say that A plus C congruent with B plus C mod M? And another one is there. A into C is congruent with B into C mod M. In fact, we can prove both of these now. But we'll remember those three equivalences here to prove. A congruent with B mod M. This implies what? M divides A minus B. This implies what? M divides A plus C minus B plus C. Agree or not? If we add C over there, it doesn't matter. So M divides A plus C minus B plus C. Don't you think that A plus C will be able to write B plus C mod M? I'll show you numerical example also. By the same method, this thing, when you are writing this thing, this implies that M divides A minus C minus B minus C. Can't you say that A minus C congruent with B minus C mod M? Yes, we can state this. So we can state easily that if A congruent with B mod M, then this will imply that A plus C congruent with B plus C mod M and A minus C congruent with B minus C mod M. For example, take one numerical example, like we are writing 37 is congruent with 24 mod 13, because the difference divisible by 13. Now, if we are doing one thing, we are just adding say 5 on both sides. 37 plus 5 is also congruent with 24 plus 5 mod 13. Why? Because 37 5 is what? This is 42 and this one 29. Okay? So their difference divisible by 13. Check once. 42 minus 29 is 13 only. Similarly, if you have subtracted, if you have written minus 5 over there, 37 minus 5 is what? 32, congruent with 19 mod 13. this case also it is true. So if you add or subtract any quantity on two sides of congruent relation, this is valid. Hope you all are doing it with me. This is very important to do it with me. Okay, that's why these classes are being arranged. You'll be doing it with me. Okay. Now, is the second also proof that A into C congruent with B into C mod M? Let us see what happens if we go by that. We are going to prove A congruent with B mod M. So this implies A minus B is divisible by M. Now take any integer. C is an integer over there. C stands for integer. You cannot suddenly add fraction on two sides. So don't you think that C into A minus B is also divisible by M? Am I correct? So this implies that AC minus BC is divisible by M. This implies AC congruent with BC mod M. It's alright. Hope you have understood. So AC congruent with BC mod M. That is also true. Clear? So if you multiply two sides by the same integer, then the relation is valid. Clear? Let us go for next one. A congruent with B mod M and C congruent with D mod M. We can add two congruencies also. See? We can add two congruencies. How to add? We are simply adding or subtracting both sides. Then also it is valid. Okay? How to prove this? Let me give you the proof and then an example. Numerical example based on it. Okay? In the previous sum, we have seen the example when adding 5, subtracting 5, divisible by 13. Multiplication I did not show you, but let me do it here now. 37, you are multiplying by 3c. It will be also congruent with the same modulus. So this implies 111 congruent with 72 mod 13. 111 minus 72 is what? This is 39. So, and this is 39 divisible by 13. So this is true. If you multiply two sides by a constant, an integer, then also relation valid. Let us go for this. A congruent with B mod M, C congruent with D mod M. You have noticed that same modulo is there. Then we can add. We can add two congruencies. Okay? How to? That A minus A equal to B plus K1 into M. You can write this. We have seen this also. A equal to B mod M. A can be written as this B plus K1 into M. Similarly, C congruent with D mod M, you can write D plus K2M. What K1, K2 stands for? K1, K2 also belongs to set of integers. They are integers. Okay? Now, we are going to add these two equations. Number 1 and number 2. So, A plus C will be B plus D plus K1 plus K2 into M. Isn't it? So this implies, wait a minute, this by our calculation subtraction has come. Okay, the second proof I am giving you now. We can write that A minus B congruent with D minus C plus K1 plus K2 into M. This is also true if you add two equations. Otherwise, there is a method I can show you that we can add B on two sides like that. So here what we have got, A minus B congruent with D minus C plus K1 plus K2 into M. So can't I say that A minus B congruent with minus of C minus D plus K1 plus K2 into M? Isn't it? A minus B congruent with minus of C minus D plus K1 plus K2 M. So what does it mean? This implies that A minus B minus this thing, I mean C minus D, is divisible by M, isn't it? Because we can write A minus B, this if you take A minus B plus C minus D, their sum is divisible by M. So what does it mean? A minus B, C minus D divisible by M. These are individually divisible by M. So you can say that A minus B congruent with C minus D mod M. Clear? So let us take one example. We have 13 congruent with 3 mod 10. We have 30 congruent with 20 mod 10. Now if you add these two, it will be 33, and this side it is going to be what? 23. That is also mod 10. Clear? 33, if you add these two, and this is 23, 33 minus 23 is divisible by 10. Clear? So you can add two congruencies if they are under the same modulo. Similarly, you can prove that you can subtract two congruencies also. It's all right? Do you understand? So you add or you subtract two congruencies under the same modulo, it will remain valid. Now third one, A congruent with B mod M and C congruent with D mod M. This we have done, sorry, this one, A congruent with B mod M and C congruent with D mod M. You are going to prove that these two congruencies can be multiplied also. Try to prove it. These two congruencies can be multiplied also. How to prove? That A will be equal to A congruent with B mod M. What does this imply? If A is congruent with B mod M, this will imply that A equal to B plus K1 into M. Check whether I have done correctly or not. This is okay. Now C congruent with D mod M. What does this imply? This implies that C is equal to D plus K2 into M. Okay? This is alright. Now we are going to prove that AC congruent with BD mod M. You can multiply these two. From there you can prove ACBD will come here. Okay? There is another way also there, that A congruent with B mod M, this implies that a minus b divisible by m. Therefore, a minus b into c is divisible by m, where c is an integer, isn't it? Now, from here you can write a congruent with c congruent with d mod m. What does this imply? That c minus d is divisible by m. Therefore, b into c minus d is also divisible by m, isn't it? Now, what about AC minus BD? You have proved that A minus B into C divisible by M. You have proved that B into C minus D divisible by M. Now, AC minus BD is what? It is AC minus BC plus BC minus BD. Now, this part and this part, you think about these two parts. We have proved that this thing divisible by m. We have proved that this thing divisible by m. This is also divisible by m. So, this implies that AC minus BD is also divisible by m. So, this implies AC congruent with BD mod m. So, multiplication rule also proved. Let us take one example. Say 13 congruent with 6 mod 7, isn't it? And 34 congruent with how much mod 7? 6. No, that's why I want to increase. Say 36. 36 is congruent with what? 1 mod 7. You multiply these two and check on multiplication whether it is valid or not. Division will not be valid, but multiplication will be valid. 36 into 13 should be congruent with 6 mod 7. How? You just multiply 36 with 13 and divide by 7. You will find that remainder is 6 only. You write 36 into 13. Then you write 35 plus 1 into 7 plus 6. What do you observe? It is 35 into 7 plus 6 into 35 plus, so I am not multiplying, I am getting it easier manner. So you see that 35 into 7 divisible by 7, 6 into 35 divisible by 7, 1 into 7 divisible by 7, 6 is the remainder. That's why 36 into 13 congruent with 6 mod 7. Division is not possible. Congruency division not valid. Division with a scalar quantity we can do, but division of two congruencies is not possible. Division with a scalar quantity also can be done under special condition, not always. We'll come one by one. Now let us go for this. We are going to prove this because all these are very useful in congruencies. I am making you habituated before starting actual sums. A congruent with B mod M, this implies that A to the power K congruent with B to the power K mod M, where K is some integer. Okay, how to prove this? Mathematical induction you have done with me in one class. Let us go by induction. Prove by induction. A congruent with b mod m. So a to the power 1 congruent with b mod m. Now in this relation mod m, this is true, this relation is true for k equal to 1. Let the relation be true for, that congruency relation be true for p, for k equal to p. P is an integer. Okay, so this implies a to the power p congruent with b to the power p mod m, isn't it? Now this is your number 2 and number 1 is here. A to the power 1 congruent with b to the power 1 mod m, and also you can multiply two congruencies. Multiply 1 by 2 b to the power, multiplication allowed, same mod is there, isn't it? So this implies a to the power p plus 1 congruent with b to the power p plus 1 mod m. So if the relation is true for n equal to k, it is going to be true for, n equal to k equal to p, it is true for p plus 1 also. So we reach the conclusion that this will be true for every positive integer k. Clear? Understood? Let us go for application now. If you do not remember the proof, it doesn't matter in number theory, for IOQM, for Olympiad or for JEE. But application is very important. Application of what? Application of the concept so far I have discussed. What are the concepts? You can sum up one by one the proof I have given, then you start proving all these things. Okay? Find the remainder when 100 to the power 100. You will just remember the concept here, just these parts I have written here. Okay? Only these parts, only these green parts you note it down and apply it. 1, 2, 3, 4, 5. Actually 4 because 1 is repeated. So let us start solving simple problems on congruency. Find the remainder when this thing divisible by 11. You know 100 congruent with 1 mod 11. Am I correct? Because 100 minus 11, 100 minus 1, 99 divisible by 11. Now we know this. Start this way. Now raising the index of both sides to 100. You can do it. Just given the proof by mathematical induction. If A congruent with B mod M, then A to the power K congruent with B to the power K mod M. So this implies that 100 to the power 100 congruent with 1 to the power 100 mod 11. So this implies 100 to the power 100 congruent with 1 mod 11. Clear? Done? Understood? Let us go for this proof. This is a brilliant proof. Prove that A to A minus B, you could have used bracket over there, divides A to the power n minus B to the power n for all positive integer n. How to prove this? A minus B divides this. This actually, you have noted this property here, no? We can write A congruent with B mod A minus B. Can you see this part? This observation we have proved also. A congruent with B mod A minus B, because A minus B divisible by A minus B. Nothing to prove over there. So with this simple observation we can get it very fast. See how to. A minus B congruent with 0 mod A minus B, isn't it? Or you can write A congruent with B mod A minus B. No difference. This thing only written over there. Now, raising the power, no, don't say power, raising the index of two sides by n. What do you get? This is congruent with where? So this implies that, this implies what? You add minus b to the power n on two sides or take it on left side, congruent with 0 mod A minus B. Clear? So this implies that A minus B divides A to the power n minus B to the power n. Hope you have understood. Nothing new here, nothing very difficult here, isn't it? Let us go for this one. This is very interesting. And these results you have already used or going to use in many cases, in many problems in algebra. Show that A plus B divides A to the power n plus B to the power n for all positive odd integers. Previous one, A minus B divides A to the power n minus B to the power n for all positive integer n. But for plus, it is going to be odd positive integer. Some of you are very smart, I know. You will be proving it by divisibility. Class 9 divisibility only it can be proved. But see how beautiful the application of congruency here. We can get in 3 steps only. How to? Can you do before I do it here? You can if you try. We just make one observation. A congruent with minus B mod A minus B. No, minus B mod A plus B. Can I say so? A congruent with minus B mod A plus B. We are remembering that definition. The difference is divisible by modulus quantity. A minus minus B is what? A plus B. A plus B divisible by A plus B. So this is always true. This is always true. Now raising the index of both sides to what? To n. Then what do you get? A to the power n congruent with mod A plus B. Agree? Agree or not? It's correct, no? So this implies that problem is there on right side. Minus B to the power n. How to deal with this? If it is minus 3 to the power 10, it is plus 3 to the power 10. If it is minus 3 to the power 13, it is odd integer, no? It will be minus 3 to the power 13 only. So this part going to be minus B to the power n mod A plus B. Clear? So what does this imply? This implies that A to add this minus B to the power n, you take on left side. This will be congruent with 0 mod A plus B. So this implies that a plus b divides a to the power n plus b to the power n for n is of the form 2k plus 1, or n is odd. Actually, I am writing in the language of number theory for all positive integers. This is always true. Clear? Now let us go for a brilliant sum here. Prove that 110 divides 120 to the power 9 plus 120 to the power n, not 9, plus 71 to the power n plus 17 to the power n plus 3 to the power n for all odd positive integers n. See how to prove this. We cannot show it at a time, just it's a difficult something. 110 dividing this, no. But we can use the concept we have just got here. This is divisible by a plus b when n is odd integer. So let us go by divisibility of 2, 5 and 11. If you are able to prove that this quantity, that 120 to the power n, 71 to the power n, if you can prove that 2 divides this, let 2 divides this thing, and 5 divides this thing, and 11 divides this thing. Let us prove it step by step. Then is the proof done, you think? Then have I proved it? Yes. They are all prime numbers. 2 is a prime number, 5 is a prime number, 11 is a prime number. If a prime number P1 divides A, prime number P2 divides A, and P3 divides A, what does this imply? P1 into P2 into P3 divides A. I hope I have explained this part. So now my aim is to prove 2 divides 120 to the power 129 to the power n, 71 to the power n, this. And we have just proved that a to the power n, this is given odd positive integer. So we can make use of the last one, that when n is odd, a to the power n plus b to the power n is divisible by a plus b. We can make use of this. N is odd. Now 129 to the power n plus 71 to the power n is divisible by what? A to the power n, b to the power n, divisible by what? Tell. This is divisible by 129 plus 71. This is 200. You agree or not? You can see that this sum divisible by 200. Why? Just we have done that a plus b divides a to the power n plus b to the power n if n is odd. Now 17 to the power n plus 3 to the power n is divisible by 17 plus 3, that is 20. We need not prove divisibility by 2 and 5 separately. It is done. 129 to the power 71 divisible by 200. So we can say that it is divisible by 10. this thing divisible by 20, we can say that this is also divisible by 10. If it is divisible by 20, must be divisible by 10, isn't it? So this one done. Therefore 129, sum of these four numbers plus 71 to the power n plus 17 to the power n plus 3 to the power n is divisible by 10. One part is done. 2 and 5 together done. Now to prove that this is divisible by 11 here, you go by this thing. 71 and 17. How much is this? 88. 129 and 3. How much is this? 132. As 11. Okay, I go step by step. I have to explain step by step. As 129 plus 3 divides 122 divides 122, no, it will be 132. 129 to the power n plus 3 to the power n. Also 17 plus 71 divides 17 to the power n plus, so this implies what? 88 divides 17 to the power n plus 71 to the power n. Now what do you observe? 132 is what? What is 132? 132 is 11 into 12. What is 88? This is also 11 into 8. So which factor is common? 11. So if we say that now 11 divides 3 to the power n and 11 divides 17 to the power n plus 71 to the power n. So this implies that This implies that 11 divides their sum. Am I correct? Hope you have understood. Isn't it? Isn't, because 11 divides this thing, and you have proved that 10 divides the same thing. So why you don't see that they are co-prime numbers 11 and 10? So by using divisibility, 11 into 10 divides their sum. It's a brilliant sum. You can set yourself 1000 sums of this kind now instantly, and you can put us, teachers, your peers in trouble. Sir, prove this thing though. Something like 331 to the power n plus 2021 to the power n plus 71 to the power n plus 3 to the power or 5 to the power n divisible by 550. Something like that. May not be, just I am telling you example. So we will be in trouble. What kind of question you are asking? Learn this, and from here you make sums yourself. Clear? Let us go for another one, which is of Olympiad standard. Previous one also. And this is a brilliant sum, I am telling. Brilliant sum. If you can prove it before I do it here, you must specify that you have done it. What is that? Why I am so encouraged, so enlightened to share the idea with you? Just see the sum here. Check. What you see here? Prove that product of first 200 positive even integers differ from product of first 200 odd positive integers by a multiple of 401. This is actually based on the product one, which we have proved for 2. A congruent with, suppose A1 is congruent with B1 mod M. A2 congruent with B2 mod M. And this way, we have done it for 2. You remember? This way, suppose AN congruent with BN mod M. So, what does this imply? A1, A2, AN congruent with B1, B2, Bn mod M. Okay, for 2 we have proved, for 3, for more it can be proved. Proving is not a problem here. Okay, proving I have showed you, but you don't need, you need application. Let us write to solve this sum. First 200 even positive integers. 2, 4, 6 and first 200 positive integers, 200 also included over there. And 1, 3, 5 this way up to what? Up to 199. Am I clear? 2, 4, 6 this way 100 numbers are there, and 1, 3, 5, 199 100 numbers are there. Isn't it? Check once. I have written all or not. Please verify it. 2, 4, 6. There are 100 even integers, and here also 100 odd integers. 100 odd positive integers. No, 200. You are wrong. I mean, I am wrong. This will be continued. This product will be continued up to, we don't need 200. 200 positive or 200 positive even. So it will be till 400. And this thing till 399. I hope now I have done correctly. Everyone can check it. Product of first 200 positive even integer differ from product of first 200 odd positive integer by multiple of 401. See how to answer this. These even integers are written. You know, this one written. Now make one observation here, that 399 and 2, what's the relation between them? Their sum is 401. We make this observation. And 397 and 4, they are also related. Isn't it? 1 and 400 also related. I mean, that is 398 and 3 also related. Can't I write that manner? So let us start with this product of first 200. 2 congruent with minus 399 mod 401. Have I done correctly? Because their difference 2 minus minus, that is 401 divisible by 401. So this is correct. Isn't it? This is your number 1. Number 2, 4 congruent with minus 397 mod 401. You understand the pattern? Then what's going to be? 6 congruent with minus 395 mod 401. Number 3, we cannot write all this manner. Let us complete here. 400 congruent with minus 1 mod 401. You agree or not? This is correct. Now all these can be multiplied, isn't it? But right side there are negative signs. How many negative signs on multiplication? 1, 2, 3, 4 this way, 200 negative signs, minus signs. So on multiplication, I mean multiplying these congruencies 2, 4, 6 up to 400, 399, 397, 395, and minus 1 mod 401, isn't it? Is that clear? So this implies that 246 so this minus 1, minus 1, minus 1, minus 1, they're all common. 399 coming in opposite order, we can change the order here, mod 401. Agree or not? So 2, 4, this is 1, 2, 4, 6 into 400 congruent with minus 1 to the power 200 is 1 only, and I am writing from end. 1, 3, 5, this one will go at the end. 399 mod 401, isn't it? All of you understand? It's a brilliant sum. You must practice. I will share problem sheets from a link from my website that I will notify. I am already prepared for that to share all the documents, whatever I have with you. Okay? Whatever I teach, mathematics, physics, I will be sharing all the documents I have made in my teaching career, one by one. Okay? Now let us start the most brilliant theorem. All people are brilliant. They all are so intelligent. Fermat, PhD Fermat, and then Euler, Gauss. I cannot keep one of them above the other. Every day I remember their work, believe me. Fermat's theorem, such a brilliant theorem, such an important theorem in number theory, which is the pillar of your success in number theory, which is the pillar of cryptography. Cryptography is a very active field of research, I will say. You have seen some application of cryptography, okay? But it is something which is infinite, okay? So, okay, let us start Fermat's theorem. This is related to prime numbers and an integer. This will relate a prime number with an integer, that is Fermat's theorem. AB integer, with number theory we take positive integers only. AB any positive integers and relatively prime to a prime number P. AP is equal to 1, then congruent with 1 mod P. Before I give you the proof, I just tell you, see how brilliant is this. Suppose you are dividing 43 to the power 40 by 41. You are dividing 43 to the power 40 by 41. What's the result? It is 1. 43 to the power 41 is a prime number. this minus 1 is congruent with 1 mod p. P is 41. Clear? So this implies 43 to the power 40 congruent with 1 mod 41. So in such a huge number, you divide by 41, remainder is 1. You get in almost in one step. This is Fermat's theorem. Proof is very interesting. I can give you proof by 3 different methods, but all are not suitable for you. But at the same time, we cannot just find the application of number theory, Fermat's theorem without giving the proof of this thing. Okay? I have to give you the proof. I have to give you the proof with the help of what? With the help of binomial theorem, with the help of mathematical induction, with the help of combinatorics. I am going to give you the proof with the help of combinatorics first. Fundamental principle of counting. Okay? How to prove that? Okay, well, I'll give you the proof in next session. Fermat's theory we won't be able to complete today. Let us find one more application and then we'll go for proving in the next session. I'm coming with the proof. Proof should be done in the beginning, not at the end of the session. Okay, let us take one very simple example. Show that 300 to the power 302 congruent with 4 mod 5. You think before I do it here? Try, think first. I give you one clue here, then you complete the proof yourself. Just you observe, make this observation. 3 to the power 4 is congruent with 1 mod 5. Why? By Fermat's theorem, 3 to the power 5 minus 1 congruent with 1 mod m. Okay? Do it. Done. You got? Have you done it? 3 to the power 4 congruent with 1 mod 5. So raising the power to 75. 3 to the power 4 to the power 75. 1 to the power 75 mod 5. So this implies 300 to the power 300. 3 to the power 300. 1 to the power 75, 1 only, 1 mod 5. Is that clear? But you haven't reached that. 3 to the power 100 and 3 to the power 302. How to get that? Multiply by 3 square on two sides. So this implies 3 square you have multiplied, 3 square into 1 mod 5. So 3 to the power 302, 9 mod 5. Dividing by 5 and you will say 9 is the remainder. No. So what you will do here? Divide 9 by 5 again. So this is congruent with 4 mod 5. So 3 to the power 302 will be congruent with 4 mod 5. If you divide by 5, remainder is 4 over there. Just one more sum, then I'll complete the session here. Just prove that 11 to the power 34. Next session we are coming back with exciting problems on these, and the concept of Fermat's theorem will be added with the concept of Euler's theorem. These two will make the thing so brilliant you won't believe. Okay, let us do it first. 11 to the power 34 is congruent with 2 mod 7. We have to prove this. You try for 1 minute, then I'll start. (11 and 17). What is the gap over there? 6. 11 square is how much? If you divide by 17, what's the result? 7 into 17, 119. Let us approach with this. 11 square is congruent with what? 2 mod 17. So this implies 11 to the power 11 square to the power 4 congruent with 2 to the power 4 mod 17. You agree or not? And why 4? Why not 17? Why the index is not raised to 17? Because 2 to the power 17 will come. It will create huge trouble. On the other hand, this is giving us a very simplified form. 11 to the power 8 16 mod 17. Okay, 16 you cannot divide by 17, but if you say that I'll add 1 and subtract 1, then it's all right. Okay, we are playing with congruencies. Added 1 and subtracted 1. Now 17 divisible by 17, so you may exclude this. 11 to the power 8 congruent with minus 1 mod 17. Now what you require? 11 to the power 34. You think how to get it? Have I got it already? Just check. No. If I raise the power to 4 on both sides, index, raising the index to 4 on both sides, 8 to the power 4 will be congruent with mod 17. What does this imply? 11 to the power 32 congruent with 1 mod 17. Not finished yet. Not finished yet, but we have reached almost very close to 34. And we have this thing here. 11 square. We have 11 to the power 32. Just we have proved 11 to the power 32 congruent with. Can't you multiply these two? Just multiply. Multiplying 1 mod 17 wait a minute, 1 no, if you multiply it will be 2 mod 17. So what have you got? 11 to the power 34 divided by 17 will give you the remainder 2. Just take one sum for practice before I share the documents with you. You just prove that, find the remainder, prove this at home, or find it at home, find the remainder when 7 to the power 32 is divided by 5. Prove it. 7 to the power 32 is divided by 5, and number 1, Number 2 is 41 to the power 65 is divided by 5. Also you can take another one. 2 to the power 1000 is divided by 17. Do try all this at home. See you next session coming with exciting problems on number theory, okay, which is important for forthcoming Olympiad examinations, which is important for, in fact, for any examinations. For your JEE preparation also, if you are doing congruency concept, it is of great help in binomial theorem. Okay, see you again. Thank you for staying with me.